So now that we know all about binomial random variables and how to find their probabilities and create tables and all of that good stuff, we have a few more highlights to hit. First thing we want to learn how to do is find the mean and the standard deviation of the binomial random variable. And this is actually going to be extremely easy. Binomial random variables, because of the way they're structured, are so simple to find the mean and the standard deviation for. The mean is this formula right here, where the mu, and of course remember these are mu because binomial is a probability distribution, and the probability distributions are always considered the entire population. So the mean is considered n times p, and the sigma, standard deviation, is n times p times 1 minus p, and then you take the square root of it. It's as simple as that. You can put them right on your note sheets for your exams, and I would recommend that you do. All right, so now we've seen this before. The Agency for Healthcare Research and Quality reports that 53% of people who had coronary bypass surgery in 2008 were over the age of 65. 15 random coronary bypass patients are sampled. Find the mean and standard deviation. Well, we saw many pages ago that this was, in fact, binomial. Let me remind you right here. It was on this one. And n was 15 and p is 0.53. So I'm going to copy and paste those later on. Actually, it's not even worth it to copy and paste. I just typed them. So then q, which is 1 minus p, is 1 minus 0.53, which is 0.47. I'm doing that in my head, but you can just grab a calculator. 1 minus 0.53, enter. Get 0.47. So there we have it. So now we have all the pieces we need. So the mean will be mu, and n is 15. There we have it. And p is 0.53. And I just wrote a little note in here just to remind you that this is a binomial experiment here. So I would just grab the calculator, 15 times 0.53, and sure enough, you get 7.95. So that's that. Now the standard deviation will be sigma, and that's the square root. So you can actually just do it all at once. Square root n, which is 15, times p, which is 0.53, times 0.47. And you get 1.933. There we have that. Okay, so what does that mean? Well, because we do have to interpret here. That's key. So if we grab a random group of 15 coronary bypass patients, because we can't ignore the 15. I highlight that part right here, and the interpret. Okay. So we're going to say in a random group of 15 bypass patients, we would expect 7.95 of them to be over the age of 65, give or take about 1.933 patients. And I cannot stress enough how important it is to actually put your number in. You can't just say the give or take part and the mean. You actually have to talk about n. So n has to be part of the system. And then x, or excuse me, n times p, which is the mean of x, has to be in there. There's your 7.95. And then give or take your standard deviation. And then you have to talk about it in terms of the context. So be very cautious. You have to make sure that you have all three parts in there. N, the mean, and the standard deviation. But all in all, it's not even hard to find, right? We didn't even have to do stat edit or anything. Just typing into a simple formula, or two simple formulas, I should say. All right, now we can not only can we find the mean and the standard deviation, we can actually construct histograms from a binomial distribution. So the following is a pre-made histogram of the probability distribution for the coronary bypass experiment described above. So if you remember, n is 15, p is 0.53, all that good stuff. Matter of fact, you know what? I'm going to highlight that in yellow. So I'm going to take this off of yellow, just because we're going to keep using those numbers here. So we're supposed to find and label the probability that exactly 9 coronary bypass patients are over 65. And then we're also supposed to Find and label the probability that exactly one coronary bypass patient was over the age of 65. All right, poof, like magic, I've done a whole bunch here. So let's look it over. So just remember from up above, because it's the same example, N is 15 because we're looking at 15 coronary bypass patients, and the probability of success is 0.53. And then I've labeled the two bars. So there's the probability of 9 right here. That's that blue bar. And then probability of 1, you can't see. That's why it's asking why does that not show up on the graph. So we'll see that in a minute. All right, now the probability of 9 is binomial PDF 15, 0.53, 9. It's an exact probability, and so you just use the number that was given. Same thing for 1, right? So it's going to be the exact same thing, but with 1 in there. So let me grab the calculator. Distribution. If you remember, binomial PDF is letter A, so if you've forgotten, letter A, 15.53. And I want to try 9, enter, paste, enter. And I get 0.1780. And then I'm going to do the same thing again, distribution, letter A, 15.53, but I'm going to type 1, enter. And that's a problem. That's scientific notation. Never tell me, by the way, that a probability is 2.04. So you will lose points. Everybody should know that the probabilities can at most be 1. So what's happening is the decimal is 4 spots over to the left. That yields us these results here. So 0.1780 and 0.0002. So now, why doesn't the bar show up? Oh, let's label those here. So this is 0.1780, and this one is 0.0002. Now, why doesn't the 0002 show up? It looks like it's 0 when you look at it on the graph, but it's not 0. What's happening is that 0 and 1 and 14 and 15, because you remember all of those are possibilities, but they're all so small that the histogram can't show them with the scale that it has here. So it's not that there aren't probabilities there, it's that they're really, really, really tiny. So let me type that up. So the graph makes it look like the probability of 1 is 0. It also does that for probability of 0, the probability of 14, the probability of 15. There are no bars there, right? And that's because those probabilities are so small, the graph can't show them with the given scale, right? You'd need a microscope, essentially, or you'd need a better printer or computer. It just can't do it. If you made it so the graph was like, I don't know, maybe even as tall as this page with, 0.0002 written out as a tick mark, then you could do it. But this scale would make that difference, that value, so tiny that it can't be drawn. It doesn't mean that it's not there, though, so be careful. So since n is 15, you know that 0 and 1, 14, 15 do actually have probabilities. It's just they're so tiny that a computer program can't draw them. Nor could you if you did it by hand. Now I want to apply the mean and standard deviation, in particular the mean, to be able to figure out which histogram is which. So it's a little bit of a matching problem. So we have each of the following graphs has n equal to 15, but they have 3 different probabilities of success. One is probability 0.2, one is probability 0.5, and one is probability 0.8. So you have to determine which is which and then explain. Now there's a couple ways we can think about this. We can just kind of think about it logically speaking. So for example, 0.8 is a high probability of success. And that means you're going to be expecting high values, right? Whereas 0.2 is a low probability of success. So you're going to be expecting low values, right? So that's one way you can think about it. And then 0.5, of course, is 50-50, so that would be evenly distributed. But there's another way to think about this, and that is that the mean is the balance point for a histogram. Remember that from chapter 3? It's been a while. All right, so the mean is the balance point, meaning it's like the fulcrum in a teeter-totter, right? Or a seesaw, or a lever, depending on what country you're from. Okay, so if that's the case, you could actually figure out where the mean would be. There, I got that to the word. So it's the balance point for a histogram. And the mean, we learned a page ago is n times p. So that means that our balance point should be at the mean. So let's think about this. The balance points would be, and I have determined that this top one, let's say I think is 0.8, and now I'm going to test myself. Now I think it's 0.8 because of this right here, but now I'm going to check it with the mean. Well, the mean is n times p, so 15 times 0.8 would yield 12. And that seems pretty reasonable, right? The mean seems to be around 12 for the balance point for this problem. Okay, let me draw you a little arrow for it. There we have it, 12. So that's about where you'd put your fulcrum, right, in order to get the two sides to balance. Now what about this one on the right? I think that's 0.2. So what would be 15 times 0.2? 3. Okay, so that would make it 3. And that actually makes sense. When you look at the graph, the lump and all the largest bars are over at the 3. Right there, right? Now look at these two. They are very different graphs, right? Because the one on the left, there's no way 3 is the mean for the one on the left. And that formula from a page ago, that's standard, right? That's never going to change. The mean, which is the balance point, is n times p for these problems. And if that's the case, there's no way that the one on the left is 0.2, because that would put your mean at 3, which would be way over here, which makes no sense at all. But it does make sense to have it at 12, because 0.8 times 15 would make 12. Similarly, 0.2 times 15 would make 3. So you can think of it as, look, high chance of success is going to put your highest values on the right-hand side. Low chance of success is going to put your probabilities at the low side. Fine. Or you can also think of it as the mean as the balance point for that histogram, and then use that. Whichever way makes you happy, you just have to be able to explain it. Now, I've been supposing all along that C is the 0.5. Let's see if that backs me up here. So if I take 15 times 0.5, I'll get 7.5. And sure enough, that makes sense, because if you look at that graph, it has a center around 7.5 or so. Right there, right in the middle. So I'm going to put the arrow down where the center of gravity would be. So here's 6, here's 7. It's this line right there. That's 7.5. Because this bar is 7, the next bar is 8. So 7.5 is right in the middle, and it's perfectly balanced on both sides. So there's two ways to make this argument. The mean is actually kind of the simpler argument to make, right? You just have to find the mean with that formula, and then you can kind of eyeball where the balance point would be. You can also think of it as in terms of probabilities of success. 0.5 would be evenly split 50-50, whereas 0.8 will have high success rates. So the bars will be over here on the high side. And similarly, 0.2 will have low success rates, so the highest bars will be over here on the low side.